Hello and welcome to the Sharcnet webinar series. My name is Ed Armstrong and today I'm going to be presenting to you programming best practices. These are going to be tips for defensive programming. If a seminar or a webinar were to have a textbook, it would be Effective Java by Joshua Bloch. A lot of these ideas are summed up in the book and from various places online. The slides do reference specifically when it lines up with the book. So, in any programming project of a non-trivial size, regardless of the skill of the programmer, bugs are going to creep into your code. You're going to have careful planning, correct practices, and simple elbow grease to reduce their occurrence, but you're still going to get them. We're going to show you today that following a few basic practices, using appropriate design patterns and systematic testing can help you mitigate the occurrence of bugs. In this presentation, I'll show you a few practices. Some of them will be simple, some of them will be complex, and they'll either help you avoid buggy code, or when it does occur, make it easier to find and debug the bugs. Now, arguably the goal of good programming practices and software engineering in general is to protect the programmer from themselves. No one writes software perfectly on one pass. You're going to write the software, you'll test it, you'll find a bug, you'll repair it, you'll get it working, then you'll tune it, which may break it again, which will restart the cycle of test, repair, tune, and eventually you may want to add to it or something will be redefined, which can also introduce more bugs. So what we're going to do is first a little bit of background on some basic programming principles and some literacy. We'll be worshiping at the altar of correctness here. Now this isn't about writing the fastest code right away. First, we want to write correct code. We want to write it clear and concise. And that way we can make it run faster later on once we already know that it does what it's supposed to do. The second rule, clarity, is particularly when you're writing the code, and this is to go through and help you find the bugs and help you correct them. The third being conciseness, and that's going to bring us into how to write correct code. Concise, by concise I mean small methods, well-chosen style, etc. Abstraction, encapsulation, and information hiding. There are three words that sound like they're talking about the same thing, but they have some minor specifics. So I'll be using them in slightly different contexts. When I'm talking about abstraction, we're talking about defining what the code does, separate of how it does it. And that's really key to writing good code, is that you want to write to a specification, but you want the specification to be separate. Encapsulation means keeping the relevant code together on various levels. There'll be various levels of encapsulation. There'll be some very specific method level encapsulation. You'll have class level, package level, and it's all about how to divide your code correctly. And third is information hiding. Well, abstraction encapsulation is information hiding. What I mean when I say that is specifically letting the end user know only what they need to know about the implementation. So at times, you may not ever tell them what or how you implemented a class. Cohesion and coupling. Cohesion and coupling gets tossed around a lot in programming classes. And you don't really understand what they mean until you get some practice with it. But we'll define them here nonetheless. Our goal being to increase cohesion and to decrease coupling. So first, keep things together that have to change together. Keep things that have to change together, keep them close together. And that's cohesion. Allow unrelated things in the code to be able to change independently, and that's coupling. And then minimize duplication in code is using these modules correctly. So write a module, reuse it. Now, while object-oriented programming is not a prerequisite to using these principles, it does imply a certain amount of language level support. In our case today, I'll be using Java in my examples, but they can be used for just about any programming language. So specifically, what object-oriented programming language support do we have? When we're talking about abstraction, In Java, that's interfaces. And that means what you're doing when you write an interface is you are making a contract with the end user. The end user could be someone who implements your library or yourself at a future date. But what you're saying is, I want these methods to do something. I'm not telling you how. And that's where interfaces come in for language level abstraction. Now, very similar to interfaces and to a new Java user, it seems almost exactly the same thing as inheritance or extending a class. What we say when we say inheritance is now we've got a class, it does something specific rather than just a contract. So when it inherits it, it's going to inherit what that class does as well as add to it. So when you're talking about Java, there's generally a bit of a difference between interfaces and inheritance. Now, encapsulation is supported by access levels. You've seen private, protected, public, and package protected. And this means that we are implicitly saying what we want certain methods and variables to be used by, or who to be used by. Private being only the person who's writing it, it's class, only that class gets to use it. Protected means that class, that package, and anything that extends it. Public is anybody, and then the default in Java is package protected, which only that package can use it. And then when we're talking about modularity, now modularity comes in a number of levels, the most obvious of which is classes. There will also be packages we're talking about and methods. So for the first part of this seminar, we're going to deal with style. Now, style is basically a number of things that you have to try and get a feel for. And what we're going to introduce here is, first of all, avoid long code blocks. And that means don't write all-encompassing methods. Don't put everything into one class. Try to keep everything as small and concise as possible. Don't worry about the loss of overhead from calling a method. You can optimize that later. Let's just avoid long code blocks and write things so that we can read it. Use naming conventions. I'm going to show you the naming convention I use. You'll see it. It's not the only one. There's a slew of them. The only thing you should do is you should choose one and stick to it. Don't switch in between or while you're coding. Prefer collections over arrays. And this is an object-oriented sort of thing. Languages have provided you with collections. Try to use them instead of using raw arrays, as if you were a C programmer. Order class variables by scope. This is one example of a number of things when writing a class. And what we're trying to say here is keep it clean. When you write an essay, when you write a paper, you organize it. When you write a class, you should organize it. And you should keep the organization in a simple, concise manner. And the one I'm going to point out today is order class variables by scope. Wrap all your variables. When you first sit down and program in Java, you have a tendency to make your variables public, your class level variables public. I'm going to say now, never make them public. Even if they're only used within a package, make them private. And then this way it makes it easier if you have to make them public later on, well, not public, but expose them to the public later on. It goes through what's called getters and setters, and we'll get into that, and makes it easier to refactor your code. And another thing here is declare variables when needed. That simply means it's another way of saying limit the scope of your variables. And I'll show you an example of that as well. So for the first thing here, avoiding long code blocks. Now it's simple to say, hey, if you've got a 500-line method, then it's a long code block, shrink it. The one that I see a bit more often is if you have a long if-else or a long switch statement, any sort of long branching statement. Instead of putting, as we see on the left-hand side here, if I equals something, do something. If I equals something else, do something else, and so on and so forth. And in order to try and give the user or the reader of my code some idea of what's going on, I've put comments before the if statements and the else statements. And what this makes is for a very long method, and it's almost impossible to understand the flow of what's going on. So on the right-hand side, I'll show you what you can do to fix it. And that is do method calls. These will be private methods. It's the exact same things that would be the blah, blah, blah on the left-hand side, but instead you've moved them into a method. So now, in public void process, you'll see that if I equals 0, then add all. I equals 1, add some, add none, else add random. And you can kind of see what's going on a bit better than if it's just some arbitrary section of code. The other thing I'd like to point out is what's missing here is that you notice that I don't have the comments over the methods. Well, I would suggest you use JUnit, or the JUnits of testing, Java docs, to create comments. You would then move your comments from inside void process over to the top of the method declarations. And then you can look specifically if you want more detail. So we've added some detail to the method name, and then we'll move the comments out to a separate document so that you can go look it up if you need to know what's going on. Now, for the second part of style, we are talking about naming conventions. Now, when I say a convention, it means it's not enforced by the language. It means that most people do it, and therefore you should do it most of the time, and it makes the things easier to read and easier to understand. Of course, as soon as you say convention, then someone's going to show up and say, well, in this case, it's not. In this case, I got a job, and they told me to do something else. Well, follow what they do. It's a convention. It's not a rule. And what we're talking about for naming conventions is how you're going to name your variables so we can understand or quickly recognize what's going on. Now, some of the things you have to consider when naming things in a class is package level. In Java, everything is typically lowercase, package level naming. The way you name your tree, like the import java.awt, if it's a private library, typically people do the reverse of their web address. So uaguelph.ca would be ca.uaguelph.packagename.classname. And that brings us to the class name. The class name is typically, in my case, different from the package name. And you want to make this shown as an uppercase first letter, an uppercase, so on and so forth. And then implements, which is sort of a class in Java, but not really, I will often put iFood. I meaning interface, in that case, food. And it doesn't matter. You can go, a lot of people just call it the same as a class with the capitalization on the front. I stole the I from C#, I believe. Another thing is, I'll be showing you later on the immutable interface. And if you use an immutable interface, then you put immutable class name. You should never have an immutable class name for an actual implementation, and that'll just confuse people. So what you want is some prequel to the class name to indicate interface. Global variables. There's something else. It's something that often is the one caveat to never have anything private, is you make it final, static integer, display resolution, and it's all in capitalization. For the space, we use an underscore, and this just makes it known so that mostly for you, when you're coding, that this is a number, it's global, pay attention to it, don't muck with it without consequences. Variable names. Now, variable names, unlike class names, and I have deliberately gone here and said flavor, capital flavor, lowercase flavor, capital color, lowercase color, capital shape, lowercase shape, to show you that the lowercase is variable, the capital is class, and this is often the case if you just want to, particularly if you're passing a parameter, that you don't want to use X. If you can't think of a name right away, don't use X, use flavor, it implies implementation of a class. The next one is methods. Now, methods are taking the same form as variables. So it's implying something inside of a class. We're going to go lowercase. For multi-word names, multi-word methods, it's called camel case. And that is except for the first word, all subsequent words are capitalized. So the 2 has a T, the basket has a B, and so forth. And I'd just like to reiterate that this is just, a lot of these are common across most people who write in Java. Different languages have different conventions. The trick is to choose one and stick to it. And that makes consistency is key for this particular style. Now, just a quick mention about order variables by scope. This just to provide some order and coherency to your coding and makes it readable. And one way of doing that, of course, is ordering the variables. Now, I've separated into private variables, package private variables, protected, and public, even though I suggest you don't do public. And the same thing you can do with methods, which I didn't include for space reasons, but just organize everything by function. It may be getter-setters first, it may be then constructors, and so on and so forth. Sometimes if you choose an IDE, it'll support collapsing of sections to support this sort of idea, but not always. Everything is a text file in the end, so you want to do it yourself, as well as using whatever the package gives you. It's trying to get at, think about your code as if it's writing, okay? And to get a certain idea and a certain style and a certain elegance to it. Now, I'd like to make one little note here for what I've done, is you'll notice getters and setters. At the bottom there, okay, let me start over. Everything here, all of my variables are private, which means that I have to provide the user some way of accessing them. And these are called accessors and mutator methods. Typically, we add get and we add set to it. So get flavor, set flavor, etc. Now at the bottom, there is only get shape. With the get shape, it's because I made shape final, we don't have to provide a setter. Or in the case that maybe we don't want someone outside using it or changing it, we'll get rid of the set. By doing this, it allows me to do things such as check the parameters of a method. When you pass in, say, you're accessing an inner array, you can check to make sure it's not less than 0. You can check to make sure it's not greater than length. If at some future date you have changed the innards, you don't have to go back and change all your other code. You just have to change the methods here, providing excellent chance for refactoring. It's almost important that you realize that this is almost not a convention as much as it's a rule. It's just that they didn't build it into the language because they want to give you a certain amount of rope to hang yourself in case you need to do it for some odd reason. But in almost every case, your default should be private variables with getters and setters. Now, reducing variable scope. This is one, it's a throwback from C, I'm going to say, where you declare your variables first and use them later. And this creates problems, and it crops up bugs and makes it harder to, makes the flow sometimes a bit harder to read. And what we want you doing now, or what you should be doing now, is declaring the variable at the last possible moment. So on the left-hand side, we have int ijk. And you have the I, the j, the I, the k, the j there in the loops. However, on the right-hand side, you can see we can declare the integer inside the scope, and therefore use the same variable for each time. Now, there's a plethora of examples, and we're going to go through one or two about how this will help you avoid bugs. Now, I'd like to point out here, this is helping you avoid programming syntactical errors. Well, not syntax errors, I suppose, but actual programming logic errors. Typically, when you cut and paste or do something like that, you'll forget to change something. So what we're going to do is I'm going to show you a couple of examples of scoping your variables to help cut down or to help find bugs. It's using syntactic sugar the way it's meant to be used. So here we go is another example, iterator. Now iterator is a different way of going through, of looping through a collection. And in the left-hand case, you'll see we have the iterator at the top, declared outside of the loop, and we use a while loop. while has next, which means while there's something left in the iterator, we pull the item out of the iterator, fruit f equals I next, that's the next item in the collection, and then we do something with it. Now, as of Java 7, I do believe, don't quote me on that, we have these for each. So for each fruit f in collection is how we read that. Do something with it. Now, this is translated as exactly the same as the iterator example on the left. It's doing the same thing using the same mechanisms. It actually translates the for statement into an iterator and then applies the while loop to it. And that's going on behind the scenes. So everything you see there on the right is syntactic sugar. It's just for show. However, we reduced a variable, which is no longer an I. We have brought the f is declared in the for loop. It's a new value of f each time. You could bring the one on the left outside. What would be a better example, I suppose. But so thus we've reduced the amount of code there to do the exact same thing, making it a bit more readable, just a bit more elegant. And that's the kind of thing we're talking about when reducing scope. Now, here's a scoping error which is caused, this is directly from the book, Essential Java, and it is typically caused by a cut and paste error. So when you're coding, you've got an idea in your head, let's write it down, let's get it, what this thing's doing. So if we look at it for a bit, what you're doing is you're filling a deck with new cards based on 2 enumerations. However, there's an error. And the error is, and it's actually a common error, is that we've gone I next and J next, which means we are incrementing the iterator on every time we add. And it's a little hard to spot because we haven't reduced scope. Now, the way to fix this then, and to make the code a little cleaner, is here. We are going to use a for each statement. Again, it's the exact same thing as an iterator, except that we've reduced scope, and we're using a bit more of an object-oriented approach, thus reducing the possibility for the bug. So let's read through this. So we got the 2 enumerations, the same as before. Arrays as list. It's actually converting a collection or the enumeration into an array. Now, because arrays are iterable, we'll go for each suit in the collection suits. We'll go for each, that's not supposed to be rank, it's supposed to be rank, for each rank, so for each suit and for each rank, add it to the deck. You'll notice we don't have the next in there because the next is managed for you by the for each, reducing the possibility of a bug there. Create a new card on the fly, add it to the deck. So the for statement, which is strong, and I recommend you use it every chance you get, and this also ties in, you'll see how these things kind of tie into each other. You tie in to use collections, not arrays, even though an array is an iterable collection, but because you can start using these things onto it. The deck, however, is not an array, it's a collection. Yeah, I'm just talking in circles. Let's move on to the next slide. So, part 2, patterns and practices. This is going to be more of the contentious stuff that people tend to disagree with. And what we're going to do is I'm going to be showing you one programming pattern and some practices you can do that will greatly reduce the bugs in your code. Now, as opposed to the first one where we're talking about style, in this one, we're talking about actual practices, things you've got to consciously do. And you've got to find opportunities to use them. Basically, so we're going to go through 4 of them here. Exceptional circumstances, and this is exception handling, when to use them, when not to use it. Null values and the evils that they represent. Overriding equals, and what you have to ensure that you do when you do. And interfaces. So, exceptional circumstances. What do I mean by exceptional circumstances? Central to defensive programming is the concept of trapping errors, or exception handling in object-oriented speak. And exception handling is needed to identify problems that the program can't handle. You have, say, a file's not there that you expect to be there. An internet connection closed at a time you didn't expect it to close. So what we're going to do is we're going to catch the exception, and we're going to catch the exception when it's useful to do something with it, i.e. display a message, ask the user for some input, asking what they want to do next. However, exceptions are not the only exceptional circumstances. We can do asserts as well, represent an exceptional circumstance. And an assert, and I'll show you an example in a moment, an assert statement is saying this should be something, if not, we're going to terminate the program. And this is done for debugging. It's things that should never occur and to protect against programming errors. These are typically in private methods while you're developing your code. You can turn them on and off when you execute your program. The next one is runtime exception, misspelt. And this is to ensure that a class is used correctly, public methods. The difference between a runtime exception and a regular exception in Java is runtimes are uncaught. You don't have to catch a runtime exception. They're not necessarily thrown. Whereas exceptions are thrown up the tree, runtime exceptions aren't. And runtime exceptions are things like a public method is out of range. So an index exception. You're accessing a collection with an index of less than 0. That'd be a runtime exception. Then regular exceptions, which are the ones you specifically have to catch and throw and try and final and all that. Those are the ones where it's things out of your control. So while you can anticipate a user trying to use your library with an index of less than 0, you can't anticipate an internet connection going down. So you're going to ask the user what do they want to do. Maybe they tripped over a wire. So you're going to let them know and let them handle it. So those are the three, and it's important to understand the distinctions between assert, which is for during development, you turn them off. Runtime exceptions are things that you can anticipate, and regular exceptions, caught exceptions, are things you cannot anticipate. There you go. So assert. To enable your insertions, you do it when you run your jar file. And it is simply with the command line flag, enable insertions. So this means that everywhere you have an assert, it'll use it. As an example of assertion, so in this, here we have a class assert example, print string. Here we want to assert the string is not equal to null. And then it will terminate the program in the case that it fails. Otherwise, print it. Now, this is during debugging, so you'll turn it off. You would no longer include enable assertions, and it won't run that, thus not affecting your runtime. An exception, on the other hand, public class assert example, throws exception. Now, if you want to ensure, so somewhere you have no control over whether or not string is going to be null, you want to throw a new, actually this is a bad example, this should be a runtime exception, throw exception. However, with the exception, you'll note that we now include the throws part right there, and that is necessary for when to indicate to the JVM that you are throwing an exception, as opposed to a runtime exception, which we'll show next. Is this still throws down here, still throws a runtime exception as it did before, except it's runtime instead of exception, but we no longer indicate that it throws. That's because this is an uncaught exception. Anybody calling this method doesn't have to concern themselves that an exception is being thrown. Whereas on this previous slide, because it's a regular exception, it's a caught exception, people have to concern themselves with that when they're using your library. So it's kind of a runtime is a bit more invisible than a regular exception. I would suggest when deciding which ones to use, I tended to go for runtime exceptions more often than regular exceptions because exceptions make your code difficult to read. They're safe, they help you handle problems, but they do make the code inconcise. And it also creates a scoping error. Anything declared inside of a try block, any variable, has to be used inside the try block because that is a level of scope. So you'll often have to declare something outside of it, assign it some value, typically null, which I'm now going to counter and say don't use null, before using it. Now null. I've been making a few allusions to the fact that nulls are evil. The inventor of the null, he says, I call it my billion-dollar mistake, the invention of the null reference in 1965. At that time, I was designing Algo, a programming language, and I couldn't resist the temptation to put in a null reference, simply because it was so easy to implement. This led to innumerable errors, vulnerabilities, system crashes, which have probably cost $1 billion in pain and damage in the last 40 years. Richard Hoare, the inventor of the null reference. For the most part, you as a programmer, particularly in an object-oriented language, can get away without accepting nulls or returning nulls from a method. This tends to get people riled up because they love their nulls. They love, what do you do when an error occurs? You typically return null, saying nothing happens. Well, we don't have to do that in an object-oriented language. We have exceptions. Should you accept nulls? Well, what does it mean to accept a null? A null, and this is what's going to differentiate the mathematical people from the computer programmers. Because a null, it means nothing. It's not an error. It's not an empty set. It's not an empty class. It means nothing. And the only time you should ever return null or accept null is when you literally mean nothing. It has no inherent representation. So a couple of guidelines to using null before I get on to what will happen when you break them. Guidelines to it. Only use null privately in a class. Use it, feel free to set variables inside a class to null because you have complete control. So you'll assume to have checked for errors or non-set exceptions. Don't return the nulls. So don't return the null as a return value. Throw an exception when nulls pass in. So don't accept nulls from private methods. Instead of returning nulls, return empty collections or return what are called null representative objects or a null design pattern. And that means it's an implementation or an interface of that object, implements an interface that represents null, but it has more meaning than just the value null. So what I mean by return empty collections. So in this class, on the left-hand side, we have a public fruit. It's an array, get fruit. So we're going to return an array of fruit. If the collection size is 0, there's obviously no array to return. We would return null. And that's the way a lot of people do it. They say, oh, there's no fruit there, return null. However, that's not true. There's something you can do in Java, which is you can return a 0-length array. So in the second example, on the right-hand side, if the collection size is equal to 0, we'll return a new 0-length array. So there's a subtle difference there. On the left-hand side, we are returning no information. Remember that. Null does not mean anything beyond the documentation. You can document that it means no fruit was available, or you can actually return something that says a 0-length array. And the handy thing about that 0-length array is we can still iterate through it. We can still iterate through a 0-length array and nothing will happen. You cannot iterate through a null. So on the left-hand side is the returning null, and on the right-hand side is returning the 0-length array. What we have to do in main when we use this method on the left-hand side is we have to get the object. Then that should be an array fruit. If f is not equal to null, so you have to check it first. It's a special case, so we can't just assume that it's returning something good. We have to check whether or not it's a real object or a null object, and before we can iterate through it. You'll notice that we have brought things out of scope as well. We've broken the other rule about maintaining variables, reducing the scope of the variables. And the second one, because we know it will always return a collection of some sort, even though the collection is empty, we can just immediately iterate through it using the for each loop without checking for a special case. So that's the first problem of null, is it's a special case. In that a null is not an empty class, it means nothing. Like literally nothing. Here's a single instance of example of null, so not a collection. we have got a class here. We'll call it basket. Inside class basket, there we have an array list. It's an array list of fruits. And we have a method that says get fruit. And as is our practice, we are saying, oh, there is no fruit. We're going to return null. So if we return null, you read the documentation, you're going to find out that we meant that there's no fruit. However, null, again, has no meaning, has no inherent meaning beyond the documentation. Else, we'll remove something. However, if you want, since it has no meaning, what you really mean is you want to know if it has fruit. So we have the array list fruit. We've introduced a new method. So what we really mean is we want to know, does it have fruit? It has fruit method. We'll return whether or not we have fruit, whether or not you are able to call the get fruit. So we are going to assume that you're going to call has fruit before you get fruit. Therefore, if fruit size equals 0, we're going to throw an exception. Else, we're going to remove fruit. Now, if you look at this, you're going to point out that, well, it's really the same thing, right? You still have to call has fruit, the same as we had to check on null. We're just doing it in a different order, and you still have to read the documentation to find out that we have to do this. Well, there's a little caveat to this one, and that's a null misrepresented errors. This particular block of code is going to throw an exception. And it's because we were supposed to check for null and we didn't. There's a little caveat there. Up on the first line here, we have called for a piece of fruit. And we call get fruit, and it's going to return something, potentially null. We're going to do some stuff. We have 10 lines. If we're ugly programmers, maybe 100 lines. And then we are going to use this variable that we filled up here, piece of fruit.eat. And that's going to throw the null pointer exception. And since we're using an IDE, we're just going to call up the stack trace. We're going to take a look at it. We're going to click through. We'll click on the line, and it's going to take us here. It's going to take us to the a piece of fruit.eat. However, that doesn't tell us anything. That is not where the error occurred. The error occurred at the top when we didn't check for null. But the IDE can't tell you that. However, if we change it to has fruit, we will go fruit. This is the second example. Basket.getFruit, but we didn't call it has fruit, the same as we didn't check for null before. Both the same mistake. We missed a line of code in both places. However, where is the exception going to be thrown? The exception is going to be thrown where it occurred, where our logic error occurred. When we call basket.getFruit, we didn't check has fruit. So the exception is going to be thrown where we made the mistake. It's not going to do some stuff before we use it because the exception is thrown already. So null has a tendency to misrepresent errors. So if you avoid returning null and you make it implicit what you want the user to do, then you can implicitly check whether or not the user has done it. So that moves us on. And there's other examples of null. But time constraints, I've got some other things I want to explain. So we are going to move on to overriding equals. Now equals is potentially one of those things where object orientation has gone crazy. It's a good method, but you really have to pay attention to what's going on. In Java, every object has equals. By default, equals is just a reference to the memory location. It means that by default, any two different implementations of an object, sorry, not implementations, instances of an object, are not equal. But this may not be the case that you want. Maybe you want strings, you want to look at a string, you want to overwrite equals for some reason. There are a number of things you have to make sure that remain true in order for the equals to still work with all the collections and to still work in general. And that is these following 5 properties, and that is reflexive. If the object dot equals should always equal itself, they should always be symmetric. So if one object equals another, that other should equal the original. Transitive, if x equals y and y equals z, then x equals z. Has to be consistent, so that means if x equals y now, then if you haven't changed the state, then x equals y always. Non-empty object, means that x is not equal to null. So if you compare x, an instantiated object, to null, a no value, no information, it should not be equals. And I would recommend that you write JUnit tests every time you make override equals to ensure that these 5 properties hold. And then your object will work properly with collections. Okay. Classes should be immutable unless there's a very good reason to make them not immutable or mutable. If a class cannot be made immutable, limit its immutability as much as possible. And this is directly quoted from the book I referenced at the beginning, but takes a little bit of explanation. What they mean by immutable means stateless. It means once you have instantiated the class, ultimately, you can't change it. This is not really the case in reality. As you're using things, you can't make everything immutable. So if you can't make it immutable, change it to make it as immutable as possible. So it makes the class simpler to use and implement. You don't need to copy. If it's completely immutable, you never need to copy the class and you never need to synchronize it. And that's because there's no changes. One instance of it is the same as another once it's created. They make good keys because they don't change. And they're never in an indeterminate state, which makes them good for parallelization. So you don't need synchronization. Some tips on how to do this is you can make your class final. By making the class final, nobody can override it and make it immutable. Make all fields final, and by fields we mean the variables inside the class, and make them private. That way nobody can go in and directly change them. If it has no accessor methods, it's immutable. So you've made all fields final and private, thus you can control them with the accessor methods. Thus, if it's not completely immutable, then you can tell how mutable it is by the number of setters. Set all set values in the constructor. So that means if it's immutable, that means all values inside the class have to be set in the constructor or by a factory method. In order to make things immutable, you need to understand interfaces a bit, or one way of doing immutability is interfaces. An interface, which is significantly different than a class, in that a class can have fields and interfaces can't. You can instantiate a class, you can't instantiate an interface. It's just a means of classifying common traits and behaviors that are potentially exhibited by many otherwise unrelated objects. So in this interface, you'll notice there are no local variables. There also are no private, public declarations. And while that typically in a class means it is package private, in an interface it is public. All methods declared in the interface by default are public. And there, of course, are no bodies. However, with the advent of Java 8, there is the caveat that you can make what's called a default method declaration, which means it has some code associated with it. This is not multiple inheritance because there is no local variables, but it is a certain given. They have their reasons, but they did it, and it's done. So remember that interfaces by default, all methods are public. And this thing down here, the default interface, is something there, and I would recommend you don't do it. We're running out of time, so I'm not going to get into default interfaces. However, so when you have an interface, what I'm getting at here is now that you have an interface, if something has an interface, code to the interface. So that means, for example, class bucket on the left-hand side there has a private array list, my list equals new array list. That is not coding to the interface. You want to use an array list, but let's treat it as a list. On the right-hand side, private lists, my list equals new array list, but you'll notice we've declared it as a list here, not as an array list. That means if we want to refactor the code, this is just thinking ahead to refactoring, and I decided that an array list is not the best option for the way I'm using my data. a tree list is. Now, they both implement the list interface, so all I have to do is go through and change ArrayList to tree list. Because I named a variable or declared the variable as a list, that means I guarantee all the code I've written was written to the interface, not the implementation, so I don't have to go through and change any code. Simply change the declaration. It's a lot cleaner, and you'll thank yourself for it when you go to refactor or change your code. And this brings me to my point, which was the immutable interface. You may have a mutable piece of code. And that is, in this case, on the right-hand side, we have some code. It does stuff. You want to be able to, at times, change it. But you want to be able to let other people have a copy of it, to look at it, but not change it. So it'll be immutable to them, but mutable, say, inside a package. So what we'll do is we will create an interface with only the immutable methods. So you'll notice they're all getters. So the get flavor, get color, get shape make no change to the state of the class. However, you, on the inside, would have public fruit. You notice on the right-hand side, there's public void ripen was the example I put there. And that means that that will change the state. Do you follow? So the stuff that implements the interface, you implementing the interface have to make sure that none of the getters change the state, and only the ones that aren't in the interface change the state. And that allows you to control which packages or where you return an immutable fruit as opposed to a fruit. And my last slide is not changing, but it's just citations. There we go. There is a website there if you'd like to go and take a look at. It contains a lot more than I covered here, and of course the book as well.